So, to trail with Newton's third law, we're going to be looking at the forces involved in motion of objects that are interacting with each other. So, for example, let's say we're moving. We have a couple of boxes. They're sitting on the floor. I'm going to call them M1 and M2. I've drawn them different sizes just to imply they're not the same mass. So the smaller one that I've drawn, let's say it is, 10 kilograms. M2, bigger, let's go with 14 kilograms. Totally making the numbers up. Let's say also there's going to be some friction. The friction, of course, is going to depend upon the material the boxes are made of and the floor. Let's go ahead and just assume a smooth floor. So the force of kinetic friction would be something small. Let's make it 0.11. If that is the case, then the coefficient of static friction would probably be approximately 0.15, because typically the coefficient of kinetic friction is approximately 75% of the static friction. That's not always the case, but it's pretty common, so it's okay to use that as a generalization. All right, let's say we have a force of push. And again, just to keep things on the simple side for a minute, let's say we are pushing on these boxes. We need to move them to the other side of the room because they're kind of in the way. And just to keep components of forces on the easier side, let's say we're just pushing with a horizontal force. I'm calling it P. Let's first find what force is required to get the boxes moving. Now I know if I push on box 1, because box 2 is behind it, my pushing on box 1 is going to cause box 1 to push on box 2, and the two of them are going to slide together across the room until I stop pushing. So we know from the last chapter that we have to push hard enough to overcome the force of static friction. And so that's what I want to first figure out. As far as we're concerned, it is totally valid to pretend this is essentially one big box of M1 plus M2. I'm suggesting they have the same surfaces, which seems fairly an okay assumption. Boxes are made of cardboard. So assuming they have the same coefficient of friction with the floor, we can essentially pretend they are one big box. We're pushing on this big box with the force P. So if they were one single object, we would approach this problem similar to the last chapter. We draw the free body diagram. This dot represents a box that has a total mass of 28 kilograms. The box would experience a force of static friction at the moment. Well, I guess the box has a normal force. The box has a force of gravity. So in this free body diagram, by calling this static friction, we're implying no motion. Because static friction means there is no sliding along a surface. So by putting static friction in here, we will be able to say it is still stationary. Now, if you remember also, say the force of static friction is the coefficient of static friction times the normal force, this is the biggest or maximum possible value of static friction. So we have a coefficient of static friction. We can certainly calculate the normal force. We know if the boxes are sliding along the floor is horizontal. We know there's no acceleration in the y direction. So we know there has to be no net force in the y direction. With only those two forces, the normal force needs to balance out the force of gravity. If there were additional forces that had y components, we would need to account for those. But in this situation, the normal force will equal mg. So I can come down here and plug in the coefficient of static friction, m meaning the mass of both boxes together as if they were one, and then g, of course, is 9.8. So if I plug that in, I'm getting 35.28 newtons. So the answer to this specific question, P needs to be greater than essentially, 35.3 newtons. Has to be greater than this value we're getting. Now technically we have 2 sig figs, so we would round that to 35. But let's move forward. Let's say I apply a force P that equals 38 newtons. 2 questions. What is the acceleration of the boxes? So question 1. Question 2, how hard does box 1 push on box 2? Now, as far as the first question is concerned, since when I push on the boxes, they move together because box 1 is pushing on box 2, I'm assuming I'm applying this force throughout the course of this question. So they will both have the same acceleration because they will be moving together. So if they're speeding up, they'll continue speeding up together. And that's going to be true as long as I keep pushing. Now, granted, I only have so far I can push. I only have so fast I can walk. So the course of this particular question is only going to be the time period that we are actually applying this force. We know the box is moving because the force P that is now 38 newtons is bigger than the maximum possible static friction force. There will be kinetic friction at this point because the boxes will be sliding. There will be a normal force up because the floor is pushing up, a force of gravity downwards. This free body diagram assumes one box that has a mass of that 10 plus 14, so 24 kilograms. In the y direction, we find that n equals mg for the same reason it did in this last step. So we know that much. But in the x direction, the net force is going to be P minus the kinetic friction, and we do expect that to result in an acceleration in the x direction. If we know we have overcome the force of friction, we know we're going to make this box move, The force of kinetic friction is going to be smaller than the force of static friction. So we know we're going to have a net force. If you don't recognize that immediately, it's okay. Just set up the equation and start approaching the problem as we have in the last chapter. Free body diagram, write out F equals ma, so the net force that is causing the object to have an acceleration. Here we know the force P is 38 newtons. The force of kinetic friction will be the coefficient of kinetic friction times the normal force, or mu mg. We know the coefficient of kinetic friction is 0.11. The mass, we've drawn this free body diagram as if it were just one big box that has a mass of 24 kilograms. And then we still need G here. So plugging these numbers in, that's going to give us the net force. That has to equal the mass of this one big box times the acceleration the box has in the x direction. So let me plug that in. Okay, so a few digits. As far as expressing my answer, I would say that the acceleration is 0.51 meters per second squared. We're going to end up needing to use the value of acceleration to answer the second part. When we do, I'm going to use this value that has a couple more significant figures just to minimize rounding errors. So again, as we look at this, we can totally just pretend this is one big box that has a mass of 24 kilograms. But I don't know if you've noticed, this second question, how hard does box 1 push on box 2? This free body diagram doesn't involve that force. If we come back to the original picture, I know box 1 pushes on box 2 to the right. I'm going to just call this F sub C for the contact force between them. But Newton, his third law, tells us that if box 1 is pushing on box 2 with this force F sub C, then box 1 is also experiencing the same force, but in the opposite direction. So whatever box 1 does to box 2 does in the opposite direction, but same magnitude of force on box 1. In order to answer questions that ask anything about the forces of interaction, we end up needing to draw free body diagrams for the objects individually. Okay, so what I mean by that is we're going to come down and draw a free body diagram for just box 1. So here, let me do this rough sketch again. M1, M2, this push. We said M1 was 10, M2 was 14, mu K was 0.11, mu S was 0.15. So I can pull out and look at just box 1 and what that box is experiencing. I know my hands are pressed up against box 1. This force P is me pushing on box 1. Box 1, of course, is experiencing a force of gravity. I'm going to specifically put a subscript of 1 on it, because I'm talking specifically about just that one box at the moment. This box experiences a normal force. This box experiences some friction. But this box also feels a contact force from box 2. Box 1 is in contact with box 2. So as box 1 is getting pushed by me, it gets pushed into box 2. So it feels that resistance to motion. So it's this contact force from box 2 that we need to account for if we are focusing on box 1 alone. Now the nice thing is the acceleration of box 1 depends upon the net force on box 1 divided by its mass. Newton's second law applies to any one object at a time. And so previously I mentioned we were just assuming it was one big box that had a mass of 24 kilograms. That's totally fine. We can find its acceleration by net force over mass simply because we were treating it as one box. Now we're like, okay, this isn't really one box. M1 is one box, so we're going to look at that by itself. Now we know the acceleration in the y direction is 0. Box 1 is sliding across the floor. It's not accelerating vertically at all. That means the net force is 0. Since we have the normal force up and simply force of gravity down, those two forces need to balance each other out. So we still end up with this relationship, in this case, that the normal force is equal to mg. This normal force will have a different value than the previous one because we're now talking about a mass 1 of 10 kilograms instead of the bigger mass of 24 kilograms. In the x direction, we know we're applying enough force to get it moving. We know kinetic friction forces are smaller than static friction, so there will be an acceleration. This acceleration is going to depend upon the net force in the x direction specifically, so all the forces along the x-axis, and then the mass of this specific box that we are talking about. We can write this as net force in the x direction is the mass of this box times its acceleration. Well, we calculated the acceleration above. Now, granted, we talked about these boxes as if they were one, but whether they were one big box of 24 kilograms or these two individual boxes, they're going to have that same acceleration. So we actually know the value of this acceleration. What we're doing is we are relating that back to the forces. So coming up to my free body diagram, net force in the x direction. I'm going to call forces to the right positive. So the push P is the force that is in the positive direction. The kinetic friction force on this box is to the left. The contact force on this box is also to the left. That needs to equal the mass of this specific box times its acceleration in the x direction. So we said the push was 38 newtons. We have calculated this acceleration. And again, I'm using a couple extra digits just to minimize rounding error. We can write this. We know the force of kinetic friction is mu times n, but n in this case is mg. And by the way, you can always plug that in to begin with. Instead of writing just the force of friction, it's valid to type in mu times n, but make sure you are calculating n correctly for the problem you are working on. So here we know the pushing force is 38. The coefficient of kinetic friction is 0.11. This specific mass is 10 kilograms. We do not know the contact force. Ultimately, this is what we're trying to find. Again, it's the mass. We're talking about the 10 kilogram box specifically, and then the acceleration that we have calculated. Turns out that this contact force is our only unknown. And so we can calculate it. So I'm getting 22.167, rounding that to 2 sig figs. We can say that box 2 specifically is acting on box 1 with a contact force of 22 newtons. It's this contact force that is not allowing box 1 to accelerate as fast as it could if it were moving on its own. Now, technically, we're done with the problem. I do want to walk through looking at the other box, though, because it technically, once we get to this, to the acceleration, we can look at the force of contact on either box. We didn't have to look at box 1 first. We could have looked at box 2 first. So I really just want to take a minute to go through box 2, just so you can see the forces and how we would set up the equations. So box 2 is, of course, feeling the pull of gravity. And by box 2, I specifically mean the 14 kilogram box, the one on the right. There is a normal force. There is a contact force. That represents box 1 pushing on box 2. There's a force of kinetic friction. There is no force P. That can be a little confusing at first. I mean, there's obviously a push, but the reason we don't include it on box 2 is because my hand is not physically in contact with box 2. So I'm not pushing on box 2 directly. When we talk about the free body diagrams, we can only include the forces that are directly acting on the object. So in this case, it is that contact force with box 1 that is responsible for making box 2 accelerate. Reasoning through the net force and its relation to acceleration, again, acceleration is 0. That leads us to the normal force on this box equaling m2g. So the 14 kilograms times 9.8. In the x direction, so writing out net force equals ma, but specifically for this box, we would say the contact force to the right minus the friction force to the left. So I'm jumping, this is our friction force. This equals mu times n. So I'm just jumping to plugging that in. Those are the only forces we have in the x direction. So this needs to equal the mass of this box specifically times its acceleration, which we've already found. So according to the free body diagram and Newton's laws for this box, the contact force should be the mass times acceleration plus the friction force. So when we plug these values in, oops. Oh, I pulled the mass out. So A plus mu G My calculator gives me 22.16 and a couple other different values, so it's a little bit different at the farther significant figures, but that's to be expected because the 0.5053 is rounded. But by leaving that value out to 4 sig figs until I'm done allows us to get and see that we get the same answer to those two significant figures. Very cool. So in any given problem, if we want to find, or if we're given forces between the objects that are interacting somehow, then we want to look at the F equals ma for the objects individually. So on the left, we looked at box 1. On the right, we looked at box 2. That is the only way we're going to see that force of contact, how those boxes are interacting. That's the only way we're going to get those forces in our equations. Now, total interesting thing. If I solve for force contact on this right side, which I already did, and I take this and plug it in for force contact in the equation describing box 1, you're probably wondering why I'm doing extra work. You'll see. All I'm going to do is go ahead and bring the MA term to the other side, and then just write this left out side out as well. Do you remember how earlier we said, let's just pretend we have one box with a mass of 24 kilograms? This is the equation we came up with that represented the net force on that one box in the x direction. And we said that had to equal the total mass, that 24 kilograms, times the acceleration. So sometimes we'll have problems involving interacting objects that it's kind of hard to pretend it's one single object. Please know, anytime we have a problem involving two objects, we can always look at the two objects individually, write out what we mean by F equals ma, the net force equaling mass times acceleration, and combine them together to relate that to find just the acceleration. But again, when we pretend and look at the object as if it was just one big box, there's no contact force in this equation. And that's because that contact force is acting individually on M1 and M2. So that ultimately means it's internal to the system. It's internal, it's between the two objects in the system as opposed to on the combination of the two boxes. So this chapter is all about interacting objects. I'll do some examples for you, as well as some concept reviews, or I guess knowledge checks, so you can see how to apply this and see if you're thinking correctly.